Welcome, everyone. Today's lesson will be on trigonometric identities. So today is what we're looking at is taking these skills that we learned in the last lesson of just introducing these identities, and we're going to be trying to prove that the identities in our examples here today are true. So let's look. A trig identity is an equation involving trigonometric ratios that hold true for all values of the variable. We're going to be using these identities that we've already looked at in previous videos. So we have our reciprocal identities, the quotient identities, and the Pythagorean identities. And we'll be using these and substituting them in order to prove that one side of our identity is equal to the other side. And don't forget also with our Pythagorean identity, we can rearrange these into different forms. So let's just start out by rearranging those. So sine, if I wanted to rearrange this so it's sine squared theta, then I'd be bringing the cosine squared theta to the other side. And the same thing if I wanted to solve this for cos squared theta, I'd be taking the sine squared theta to the other side. And once again, when we take them to the other side, we'd be changing their signs. So we could also use these identities as well to help prove our trigonometric identity. So when proving our identity, we transform the right side of the identity into the left, or we do the opposite. We change the left into the right side of the identity, and we must manipulate these equations independently of each other. So it's not like I did here, bringing one side to the other to isolate. We'll just specifically be looking at one side, the left side of the equation, or the right side when we're trying to prove these identities. Now, this is a topic that a lot of students, they might struggle with at first because there's not just one recipe in order to solve these identities. We might each solve the identities using a different method, but the whole point is to make your left or your right side of your identity look like the other side of the identity. So we're going to, once again, use a few steps along with our identities in order to guide us through these questions. So some of the steps we're going to be using, we're going to simplify the more complicated side. So we'll decide sometimes one isn't more complicated than the other, and we'll just pick a side to start with. Write all expressions in terms of our sine and cosine. Apply the Pythagorean identities where appropriate. So we have those Pythagorean identities. Once again, with the sine and the cosine, we can use our quotient identity for that. Other skills that we're going to need is use a common factor, a common denominator, we're going to be factoring. We might need to expand or simplify. Another thing we did in the last is we might multiply by the conjugate. So we might use that concept as well. Remember, multiplying by the conjugate is this: we have a binomial of some sort. Say we have cos theta minus 1. The conjugate of that is we just have the same two terms in the binomial, but we change the sign. So we might use this concept as well, where we're multiplying by the conjugate in order to make one side of our identity look like the other side. So once again, be patient with yourselves. It does take a little bit of getting used to doing these problems. Remember, we might look at it in different steps. So, just look for the pattern. Give yourself, time to just practice these and let it sink in. So let's do a few examples here together. Prove that tan squared theta plus 1 is equal to secant squared theta. So we have to prove that one side is equal to the other side, and this is for all values of theta. This would be true for. And remember, we can't be taking values like the 1 and bringing it to the other side, or bringing this. when we prove these, we actually separate them. So I'm going to decide for this one, I'm going to say this is my more difficult side. It wouldn't matter. You could say the other one. And so this is the left side of my equation. So I'm just going to write the left side down. So the left side of my equation is tangent squared theta add 1. And I'm going to work with this expression, and I'm going to try and make this expression look like the right side. You're always looking back and forth to see what you might be able to do to make one look like the other. But to do that, I'm going to follow the guidelines or steps that I have here. So first, I'm calling this my more complicated side. Rewrite all expressions in terms of sine and cosine. So I can apply this to this identity. So I'm going to rewrite my tangent squared as using my quotient identity. Remember, we have our quotient identity right up here. I'm going to rewrite that as sine squared theta divided by cosine squared theta. Add 1. So let's go to our next step. Apply the Pythagorean identities where appropriate. So this is a place that we could decide to use the identity, or we could come to this step where we use a common denominator. We could factor and expand. Lots of times when I have two different terms here, I generally like to find a common denominator and work from there. So someone might see to do this differently, but I'm going to find a common denominator here. And I know if I want to find a common denominator here, I'm just multiplying by cosine squared theta on my 1. So I would have sine squared theta over cos squared theta, add cos squared theta over cosine squared theta. So combining the numerators, I have sine squared theta, add cosine squared theta divided by cosine squared theta. Now when I look here, I have sine squared theta add cosine squared theta. And if I look at my trigonometric identities, I know sine squared theta add cosine squared theta is equal to 1. So on the next step, I would be applying that. Instead of writing sine squared theta cosine squared theta, I'm going to write a 1 for my value in the numerator over cosine squared theta. Now that I only have one trig ratio, and I know I want to make it look like secant squared theta, and I know there's reciprocal identities, and I know that cosine theta is equal to secant theta, therefore secant theta squared will equal to cosine squared. So I know 1 over cosine squared is equal to secant squared theta. And I also know that my right side, remember the right side of the equation is secant squared theta. So since both sides are equal secant squared theta, I've proven that identity. So remember, you're just working with one side, the left or the right side, making sure at the end that one side will equal to the other side. So let's give another example a try. So once again, we have a left side and we have a right side. And simplify the more complicated side. So it would be your choice, which you see here as more complicated. And once again, you can do something with the left side and then move to the right side. You just can't move from one to the other. So right off when I see my, my left side of my equation here, once you've memorized these identities, these become more obvious. But if I look at my left side of my equation, I'm just going to simplify this side. It's not necessarily the side I'm going to work with, but I see that I could simplify this right away by looking at my identities up here, because I know 1 minus sine squared theta is a Pythagorean identity of sine squared theta. So I'm going to take my 1 subtract cosine squared theta, and I'm going to apply that trigonometric identity, or Pythagorean identity, sorry. I'm going to write it as 1 as sine squared theta. Then I'm going to move to my right side. So I have sine theta, cosine theta, and tangent theta. This to me is the more complicated side. I just did this because I could see right off that I could apply that Pythagorean identity. But when I look at this side, since I have the three different ratios, I want to work with this side. So rewrite all expressions in terms of the sine and cosine law. So right here I have sine, I have cosine, but I have the tangent. So I'm going to apply up here my quotient identity and sine theta, cosine theta. And instead of tangent theta, I'm going to apply my quotient ratio of sine theta over cosine theta. Now, these are multiplied and divided. So once I have a multiplication statement, remember, I can cross reduce. So I know cosine theta divided by cosine theta will just be equal to 1. I have sine theta multiplied by sine theta, which would be sine squared theta. And as you can see, my left side is equal to my right side. So I have proven that trigonometric identity. So C. If I look at both sides of this identity, I mean, they pretty much look similar. I wouldn't say necessarily that I think one side is any more difficult than the other side. So I probably will just work with the left side here to prove this particular identity. Things that I noticed just when I'm looking at this, because I'm always thinking of the different steps I would use in order to simplify these. These look somewhat similar. One looks like the reciprocal of the other, right? Like we have sine in the numerator, sine in the denominator. So I'm always going back and forth and just comparing and looking at the two as I go through and just try and rearrange or substitute things in order to make the left or right side equal each other. So I'm going to choose the left side to work with here. And let's just go through our different steps. So I've decided this is my more complicated side. I'm going to write all the terms in terms of sine and cosine, which they already are. I could apply a Pythagorean identity if I see that, but remember, we need squares for that. We don't have any squared values here, so I can't apply the Pythagorean identity. Right here, I only have the one rational expression, so no common denominator. There's no factoring here. There's no brackets to expand. I'm just going through the list. And then I wrote down multiply by the conjugate. And this is the time where you would want to multiply by the conjugate. In the denominator here, I have a 1 add cosine theta. I noticed on the right side, I had a 1 subtract cosine theta, which is the conjugate of this. So working on this side, I'm going to multiply by the conjugate. Remember, the conjugate is just the two terms, but we have a different sign in between. If I multiply the bottom, remember, I would also have to multiply the numerator by the same conjugate expression. So on my next step, I have sine theta is equal to 1 subtract cosine theta. And remember, this would be in brackets. Whenever we have a binomial, we would have it in brackets. If I multiply the first two terms here, I would have my 1. Remember how the conjugate works? My inside and outside terms, remember, one's a negative, one's a positive, so they would cancel. And then I would just be left with the outside terms here, so a positive and a negative and cos squared theta. So now I look down here and I have 1 subtract cosine squared. Once I see the cosine squared, I look back to see if I can use the Pythagorean identities, because those are the ones that have the squareds in them. And I recognize that 1 subtract cosine squared theta is actually equal to sine squared theta. So I'm going to substitute that into the denominator. So instead of having 1 subtract cosine squared theta, I have sine squared theta. So now we will be able to reduce, because we have a sine theta in the numerator, right? That is a factor, and we have sine squared theta. So this will cross out and we'll just be left with the sine theta in the denominator. So I have 1 subtract cosine theta divided by sine theta. And my left side is the same as my right side. So I have proven that identity. So D, we have sine squared theta subtract cosine squared theta is equal to 2 sine squared subtract 1. Once again, it would be your choice, maybe which you see as the more challenging side here. So let's just look. I see a couple a sine squared and a cosine squared, and I just have 1 over here. So not sure which side you want to use. I think I will just pick my left side for this one. Or maybe I should just pick the right side since I keep picking. Anyway, I'm going to just pick the left side. So my left side is sine squared theta subtract cosine squared theta. So I've picked which side I'm going to start with. Once again, it's already in terms of sine and cosine, so I can't use the quotient ratio. Apply a Pythagorean identity if possible. So here's my left side. I have sine squared theta, cos squared theta. But when I look at the right side, I notice there is no cosine squared theta on the right side. There's only a sine squared theta. So I don't really want on the left side to have this cosine squared theta, because I notice that my right side doesn't have that. So I'm going to substitute using the Pythagorean identity, so I eliminate this cosine squared theta on the left side. So where I have cosine squared theta, I'm going to substitute in a Pythagorean identity, and I know cosine squared theta is equal to 1 subtract sine squared theta. Remember, you always want to be looking from one side to the other, even though we can't work from one. We just look because we want to make one side look like the other. So noticing that there's no cosine squared theta here, that's why I'm substituting in. So now it's in terms of sine squared theta. Now we can remove the brackets. So I have a -1, a negative and a negative, so I'll have add sine squared theta. And then I can collect these two like terms. I have 2 of those, so 2 sine squared theta subtract 1. My right side is 2 sine squared theta subtract 1. So my left side equals my right side, so I've proven that identity. Whoa, so now we have E. I don't think we'll have to make much decision for this one, which is a more complicated side. So we have this rational expression here equal just to sine x. So we will be starting with our more complicated side here as our left side. So let's write that down. Once again, I'm just going to follow through the same steps. I pick my side, and we could write all terms in terms of sine and cosine. So that's my next step. I know I can write the tangent using the quotient identity of sine over cosine x. And I also know secant using my reciprocal identities is 1 over cosine. So that will be my first step, is applying that. So I know tan is sine x divided by cosine x divided by 1 add, and I know secant x is 1 over cosine x. So once again, we'd want to simplify our numerator and simplify the denominator. So you could do that by finding a common denominator here for our numerator and a common denominator for the denominator. So that's one way you can do it. But I'm noticing that I have the same, I'm going to have the same denominator in this expression as I will here. So another way I could do this one, instead of finding a common denominator up here and a common denominator down here, since I know both common denominators are cosine x, I could just multiply the numerator here and denominator by cosine x. So I could take this and multiply by cosine x. Remember, because if you multiply something by the numerator of an expression, you have to multiply by the denominator. Or you can find the common denominator here. So I'm just going to do it in this method. So now I have cosine x. Remember, it will be distributed to both of these. So I'll have sine x multiplied by cosine x. And when I multiply here, remember these will cancel, and I'll just have add sine x divided by, I'm going to multiply this by 1, so I have cosine x, add, and when I multiply here, these will cancel, and I will just have add 1. So going back and looking at, remember I have to have this equal to sine x. So I do notice I have sine x in my numerator, and I have two terms. So we could use a factoring here. I could factor sine x out of both of these terms. So sine x, I'll be cosine x when it's factored out of the first term, and an add 1 when factored out of my second term. And then we could cancel these, right? Remember, this whole expression can cancel with this expression, and I'm just left with sine x. That is my left side, and my right side is sine x. So I have proven that one side of the ratio, one side of the trigonometric identity is equal to the other side. So there is a lot of learning in these examples. You just have to be patient with yourselves as you're going through and trying, like I did, just to follow those guidelines or steps for each of these different identities, and just you know, making sure that you are very familiar and memorize the reciprocal, the quotient, and the Pythagorean identities.